it's safe to estimate that Tn is bounded by theta n squared. Okay, so this is like a recursion tree. So you can see recursion tree and the substitution method, they work for different type of recursion. Of course, we didn't try different type of recursion for substitution method. Okay, but obviously, if you look at substitution method, you can see that it can be applied to other types. Okay, other types. Or you can put it in this way. You can put this one. You can try to solve this one. Because here we already solved it by recursion tree, right? Now you can use this one as a, what should I say, like as your guess in substitution method. Okay, and try to solve this one. This is like, as I said, it's metric. I mean, a little bit like a non-traditional, should say non-traditional. It doesn't look like what we usually get like the recursion from the recurrence relation from like divide conjugate. Okay, so you can try to solve this one by substitution method by using this n squared complexity. This is a type 1. Okay, so that's pretty much about it. And the last one is a method or method theory. Okay, or method theory. So basically, it's kind of like a theory, or you can say it's a tool that can be used to solve like the recurrence relation. But it only applies to recurrence relation of this form. Tn equal to A times Tn divided by B plus f of n. Okay, and also A has to be greater or equal to 1. B has to be greater than 1. And f is asymptotically positive. Usually, okay, I mean, you usually will get a recurrence relation like this when your algorithm is divide and conquer. So this is like especially important for when you solve the divide and conquer algorithm. Okay, so and therefore, and this is usually the case for divide and conquer, and f is asymptotically positive. This is always also like pretty much always the case. Okay. Then we discuss there are 3 cases. Okay. You compare f of n with n to a power of log of b, t as base a, log of b base ba. Okay. So if fn is big O n log of base ba minus epsilon with some constant epsilon greater than 0. Okay, or put it another way. Okay, fn grows polynomially slower than n log base ba. If that's the case, then t of n is theta n log ba. Okay. So this is the first case. The second case, if fn equal to theta n log base ba and log n to the power of k for some constant k. Okay, in other words, fn and n log of base ba grows at a similar rate because log n to the power of k is sublinear. And this is sublinear. If this is the case, the solution T of n is theta n log base ba times log n to the power of k plus 1. Okay, this is second case. The third case is a little bit complicated. Okay, so if Fn is omega, so this is lower bound, n log base Ba plus epsilon, okay, where this is epsilon is some constant greater than 0. In our Fn grows polynomially faster than n log base Ba. Okay, if that's the case, and we need one more guarantee. We call it regularity condition. A times f to the power of f of like n divided by b. So this one. This one. A times t n divided by b. This term. Well, I should say this. You replace t by f. Okay. A times this one is smaller or equal to c times fn with some constant c smaller than 1. Okay. We also need this guarantee. This is regularity condition. Okay. If we have both cases, both conditions, then T of n will be theta Fn. This regularity condition usually works. Usually it's there. Okay, usually. But you should write it. You should at least like check it. Okay, but it is like usually the case. So some example. T of n equal to 4 times T of n divided by 2 plus n. I think we have this, we have seen this one, right? We use the substitution method to solve this one. And I mean, as this is the first example used for the substitution method. We know that pi bound is n squared, right? Big O n squared. Okay? And so we can see A is 4, B is 2, right? And then this is your f of n. So n log base Ba is n squared, right? So Fn is n. So this n squared is polynomially grow faster than f of n, right? So this satisfies the case 1. So T of n equal to theta n squared. Okay, you can directly write it out. Okay, why? Because the master theorem has been proved. Okay, other people has done that. So you don't need to prove master theorem again. You could, and I highly encourage you to do that. Okay, but we will not talk about the proof of the master theorem in the class, but I will give you like intuition, okay, of master theorem by the recursion tree later, okay. So this is the first example. Then next example, we don't change this term, but we change like the f of n. So T of n equal to 4t n divided by 2 plus n squared. So you can see that, A is still 4, B is still 2. N to the power of log base Ba is n squared, as we already know. So this n squared and f of n is n squared. So they are, polynomially grows like with the same rate. In this case, okay, and also like f of n, you can write it as n squared times log n to the power of 0, right? Which means k is 0. So T of n will be n squared log n. Just add 1 to the power of k. Okay, that's it. Okay? So, case 3. Case 3, again, we don't change this part. We only change n, the f of n. We change that one to nq. So again, a is 4, b is 2. And n to the power of log base ba is n squared. So fa is nq. So obviously, fn is like, one polynomial. Fn grows faster, polynomially faster than the n to the power of log base ba. So, and also we need to check the regularity condition. So 4 times f of n divided by 2, which is nq. So n divided by 2 to the power of 3. I mean, is it small or equal to c times nq? Okay. Can you find the c greater than 0 to satisfy this situation, this inequality? So obviously, regularity condition holds because you can easily find c to be 1 over 2. Again, there could be other choices for c. As long as you make sure this inequality holds, then your regularity condition is satisfied. Then if that's the case, then we have T of n equal to delta nq. Basically, f of n. Okay. So, master theorem is a good tool. Okay, you can use it to prove, like, to show the time complexity of of some recurrent relation really fast. Okay, as long as you check some condition, you check, like, which case is satisfied, and you can directly write the result. You can just say, like, based on master theorem, we have this conclusion. So you don't need to prove that, which is obviously a benefit, right? I mean, you save you time, save everybody's time. But let me remind you once more, okay, once again. It only works when your recurrence relation is of this form. So for example, if you want to solve this one, you cannot use master theorem, obviously, right? Okay. The second issue is that even sometimes when your recurrence relation look like so, I mean, it does not fit into any of these 3 cases. It is possible. It is possible. Okay? I mean, especially when f of n looks ugly. Okay? So, for example, in the case 2, your f of n has to be written as, like, with certain log, right? Log over. Sometimes it may not be as convenient. And especially for the case 3, the regularity condition does not always hold for certain choice of f of n. Okay, so when the shape, when the form of your the recurrence relation satisfy this format, is it guaranteed that you can use master theorem to solve it? I would say most likely, but not always. Okay, not always. Okay, so that's the only thing I can probably tell you. Okay, I can probably tell you. So that's the limitation of the master theorem. Okay. The last one. P of n equal to 4T n divided by 2 plus n squared divided by n log n. So A is 4, B is 2. We have got to mention all this. So n log base BA is n squared. F of n is this one. So you can see, I was talking about master theorem. In some cases, it doesn't work. Why? In this case, okay, because this f of n grows asymptotically, slower than your n log base BA. Okay, because there's an order of log n difference, right? But it's not polynomially slower. So what does it mean? It doesn't fit case 1. It doesn't fit case 2. Right? But for case, doesn't fit case 1, doesn't fit case 3. So it fits case, so does it fit case 2? What is case 2? Let's go back again. Case 2. Okay. This log kn, the k has to be greater or equal to 0. And that case, the case that we observe, that k is -1, right? So unfortunately, it doesn't fit the case 2. I mean, this Fn and n log BA grows at a similar rate. You could say that. Yeah, the Fn grows slower than n log BA, but only slow by sublinear, right? Like by a log n, like order. So this one is usually it is satisfied, but the issue is this has to be log kn where k is greater or equal to 0. So there are cases, actually, especially case 2 and case 3. Okay, there are situations you cannot apply master theorem. Okay. So here, okay, so mathematical theorem does not apply. In particular, for every constant epsilon greater than 0, we have n to the power of epsilon is omega log n, meaning this log n is lower bound of n to the power of omega epsilon. So, I mean, this even when this epsilon is very, very small, the log n still grows slower than. So log n is what we meant by sublinear. It can never be grows as fast as n to the power of certain positive order. Okay, even when this order is very, very small, it doesn't matter. This one is log n is going to grow slower. Okay, so this is the case where method doesn't apply. So the idea of the method theory, how do we get the method theory? Basically, Fn, okay, I mean you try to, Tn, you try to replace it by, Fn and then expand it to like a T of n divided by b, right? So this is like you expand, I mean, try to look at this. This is T n divided by b, T n divided by b, and so on. And then you expand it once more. You get f of n divided by b, and then you have like Tn divided by b squared, Tn divided by, and so on. Here you have like a number of terms. This one you have a number of terms, and so on. So this is like the basic idea of master theory. I mean, when you use the recursion tree to try to explain, okay, the master theory, okay, and so on. So eventually, it will grow, it will shrink. I mean, to the key of 1, right? Okay, and then, okay, so you have like f of n. This one is like you have a number of f of n divided by b, and this level you have a number of f of n divided by b squared, blah blah blah. So if you look at here, the first one is f of n. The second one, because you have a expanded a times, so you have a times f of n divided by b, and one additional level, you have a squared times f of n divided by b squared, right? Okay, so the order here keep increasing by a, but the n keep, gets divided by b, layer by layer, right? Right? So this is how it works. So eventually, and the height. What is the height? Height is like this n each time gets divided by b, right? So eventually you reach 1. So basically the level of this tree is divided by log of base b n, right? Very, very obvious, right? And then, okay, how many number of leaves? Number of leaves will be, let's assume this is 1, okay? This is 1, or, well, just count number of leaves. So it will be a times a to the power of h. Why? Because each level, the number of terms gets increased by the order of a, right? So, for example, this level we have a terms. The next level we have a squared terms. So, blah, 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 to the leaf node, we have a to the power of h terms, right? Then ah, we just know a to the power of h. This h is log bn, right? Log bn, so you put log a to the power of log bn, and then in your high school, right? High school teach you, this is going to be the same as n log base ba, right? 就是我们高中学的换底公式啊 ，log 的换底公式，就是 a to the power of log bc 跟 c to the power of log ba 是一样的。我们高中有学过的换底公式，对不对？怎么样证明？还记得吗 ？Do you know how to prove that？ 忘了，你告诉老师，数学老师会哭的。对啊，我不是在讲微积分呢。I'm not talking about calculus. I'm talking about high school math. It's not like something like very advanced. Yeah. But anyway, okay. If you forget, okay, fine. Okay, try to pick it up. Okay. I mean, you can try to prove it by yourself. Okay. Actually, it's very easy. You get log. I mean, you want to prove this one equal to this one, right? You try to get log by both sides. You will find that when you get log, it's the same. So if A and B, when their log is the same, of course they are the same, right? So it's something like that. You can try to do it yourself. It's a very easy proof. Okay. 就是你就把两边取 log， 它们会是一样的，因为你取 log， 它那个指数可以拉下来，对不对？拉下来，一拉下来，你发现这两个就乘起来，这只是乘起来的交换而已。那既然是一样，取 log 两个一样，那当然它原来的值必须要一样，对不对？就这样子，非常非常单纯。对，anyway, okay, so this is number of leaf nodes. Okay, or put it another way, if you count the cost for the leaf nodes in total, it's going to be n to the power of log of base BA times T of 1, right? Then this T of 1 comes from here, right? Okay, comes from each leaf node. So, then, the case 1, the weight increases geometrically from the root to the leaf. Okay? So the leaf holds a constant fraction of the total weight. So if the case 1 is like how should I say, like this part is more important than the top one. Okay? Because each one we have this is like of course they are all costs, right? They are each of these will be the cost. I mean you need to add them up, obviously, right? So but you know some terms are more dominant, right? I don't know, more dominant. So for example, like this one, the case one is the root, the leaf nodes. I mean these leaf nodes are more dominant. So that is why, okay, this one, because T1 is pretty much can be, when you talk about order, it's nothing. So that's why theta n log BA will be a complexity for the whole thing. Okay, because dominating term is at the leaf nodes. Okay. Another case 2. Case 2 is like the weight is approximately the same for each of them. So each level is approximately the same. So that is in other words, so this level is log Bn, right? So each level is roughly the same. So so the result is this one times log Bn. So that's like what we have. Each level is roughly the same. It's exactly the case like merge sort. Remember merge sort? Each level gives you like n, right? And the number of levels is log. Yeah, so it's n of the total. Right? That's case 2. Case 3, the dominating term happened at the root. Okay? The dominating term happened at the root. So that is why, okay, the order is, you just need to consider this element. The other term, even when you add them up, they are bounded by n. Okay? So that is like, this obviously, this is not a formal proof. Let me repeat. This is not a formal proof. Okay? It just gives you intuition. If you want really formal proof of master theory, I believe that the textbook gives you like, formal proof here. Okay, you should like read it out, okay, by yourself and try to learn how to formally prove like this method. This is one of the most very important like theory. Okay, anyway. Okay, so that's pretty much about it.